Hey everybody, welcome back. This is going to be day 4, Big Friday of the first week. We normally don't have class on Fridays, but we're going to today just because of the Labor Day holiday. So welcome back. Today's session shouldn't be quite as long as the normal session, as sometimes we go past the second hour. We've got 2 brief topics today. We're going to start off with troubleshooting IPv6 network connectivity. I know that's not everyone's favorite topic, IPv6, and I know it's not something that you're probably going to be putting into use later this afternoon. So there's that. We're going to see, I gave you what I had, right, in terms of, there's ping, but sometimes ping gets blocked, so we check the ARP cache, and I told you about the hit counts and the ACLs that are sometimes, you don't always see the hit count go up because it's being processed in hardware or software and it's not registering. It really depends on where the ACL is placed and the particular version of hardware and what type of ASICs it's using. It's complicated, but in summary, if you're not seeing hit counts on an ACL, it's time to look at the configuration for that device and see if you should be. We talked about traceroute, we talked about DNS, we talked about ICMP. So with IPv6, you're going to see that it's not a whole lot different. We'll cover that in our first section, which shouldn't be too long. Then we will take a look at EIGRP, and that will be in the second session. So without any further delay, let's go ahead and get rolling. We're closing, like I said yesterday, we had covered troubleshooting IPv4 network connectivity. So now we're going to look at IPv6 network connectivity. Remember that with IPv6, you still use slash notation for most of your masks. The typical network mask that you'll see on an IPv6 interface is going to be /64. I mentioned within the ICND1 class that IPv6 is about 15 years old. But even so, it's still not fully baked yet. There's still a lot of development happening, a lot of changes, and still a lot of debate about what's appropriate. There's some vendors who have adopted a solution that says /64 is the longest mask that you should ever have, yet other devices will allow you to actually put in a subnet mask that's longer, like, for instance, a /126, maybe for a point-to-point interface. It seems from what I have seen that the majority of folks are kind of standardizing on this use of a /64. So every subnet would be a /64. So you'd have 64 network bits, and then you would have 64 host bits. Now, the way that it actually breaks down is that your organization would be assigned a /48, and that's going to come many times from a service provider, unless you go to IANA and get provider-independent addressing. Provider-independent addressing is what you would have if you're a larger organization. So if you look at Cisco or HP or Apple or Microsoft or Ford, those guys actually own the public IP addresses that they're using. They've got their own IP address block that belongs to them. Me, for instance, I have static addressing in my house, but it comes from Verizon. So my provider assigns me an IP address, and should I ever leave Verizon, those IPs go away and I have to change all my DNS. Larger organizations buy IPv4 address space, and then that address never changes. They just use BGP to advertise that block of addresses to a carrier. And you typically do it to multiple carriers for redundancy. So with IPv6, everyone's going to get their own block of IP addressing if you want it. It could be provider independent, and that's where you've got your own addressing that you broadcast out to the world, or you could receive it from a service provider. Right now, just like my IPv4 space, I get my IPv6 space from a service provider. And that service provider is a tunnel broker. I use Hurricane Electric or HE.net, and all you have to do is ask them. The tunnel broker themselves is going to be typically assigned a /32. This is what would go to a service provider, and what that would look like in terms of IPv6 might be 2600 ABCD. Each of these blocks, remember, is 16 bits. So this would be a /32 prefix. As a customer, this is what a service provider would get assigned, and then they'd start handing these blocks out to customers in a /48. So if you're the first customer, you might be assigned this first block of ABCD 0001, which we can of course break down to simply use a 1 there. And that would be an example of a /48. How are we doing so far? Your entire site would be 2600 ABC 1. This would be the 48-bit prefix for your entire organization. And then every subnet that you create from here out would just have that 4th block populated. So right here, this is where I tend to put the VLAN. Now, your typical switch can only have up to 4,000 VLANs, and we've got room for 65,536 values here. So we could have lots and lots and lots of variable address assignments here, but if you don't have 65,000 subnets, you could just put the VLAN ID in this block and it makes it easy. So if it's my router for VLAN 10, I'd say 2600 ABCD 1, and then I'd put the VLAN here. Now, if you want to get fancy, you could convert it to hex, which would be 000A. Remember, A is a 10 in hex, and you could abbreviate that by getting rid of all those zeros. And then we can make the router .1. So his address would be 2600 ABCD 1A : 1. Did everybody follow how I just got there? This is the /32 down to the service provider. That's the /48 that was our org. This got us to /64 because our VLAN or broadcast domain is going to get a particular address assigned. In this case, it's an A. And then for the last 64 bits, we just made it 001. So again, to make that a little bit prettier, here's our router. We're going to say IPv6 unicast routing. We're going to come into this interface and say IPv6 address 2600 ABCD 1. And because this is in VLAN 10, I decided to use a hexadecimal 10. /64 would give me my subnet, and my host IP is .1. So the full address is 2600 ABCD 1, and again, that gets you to a /48, which comes from the provider. This is the piece that you assigned for the broadcast domain, and I can make my router .1 just like normal. I might come over here, add my switch, add my various hosts, and just as a quick recap of what happens with IPv6, when these hosts turn on, if IPv6 is enabled on the host, and you can tell just by looking, right? We can go to our computer, and we can go into come on, Windows, quit goofing with me. I was just trying to get the control panel to come up, and I can look at my network cards and go to my adapter settings, and I can look at my TCP adapter. I can go to properties, and by default, you'll see that IP version 6 is selected here. General rule of security is if you're not using something, turn it off. You can just deselect it and hit OK, and there's no IPv6 support. But so long as you have that box checked, this is what your computer's doing constantly, whether you're aware of it or not. He's sending out route solicitations. This is a multicast to all the routers saying, hey, where am I? That's basically it. He's just asking for addressing information. And when a router has an IPv6 address, he sends out route advertisements. He advertises the prefix. So he says you're on the 2600 ABCD 110 network. And I was going to make that an A, /64. So this is what the route advertisement looks like. Sorry, that A is not a little bit cleaner. Clean that up. We can do better. Any questions so far? That's my /64. That's the subnet, and we advertise that to all the internal hosts. They see that, and they go, cool, I've got the first 64 bits. I just need to add 64 bits to get 128, and I've got a valid IP. So this is what's happening behind the scenes. Everybody okay? We covered this in ICND 1, but I know for a lot of folks, this is the first time you look at it. So I just want to make sure, not everybody's a huge fan of this, and it's tough to remember if you don't go out and implement it right away. But the more times you see it, I think the easier it gets to look at, especially when you realize that the first 48/48, and sometimes, like I've got a buddy that works at EMC. He's doing an IPv6 rollout at EMC. They got a /40. So you can get a larger prefix based on the size of your business, but just that /48 gives you over 65,000 subnets with 64 bits worth of hosts inside of each subnet. What is the IP address of host A? Well, he would dynamically figure out if this is a Microsoft box, this is going to be a random value, and it's going to change throughout the day. Microsoft used an implementation called privacy addressing. So the last 64 bits will be randomized, and then several hours later, they'll change again, and then several hours later, they change again. What's kind of neat about this is you'll wind up with multiple addresses. You'll have a new address, which is more appropriately called a preferred address, and you'll have an old address, which they call a deprecated. The old IP address that you had originally, before you came up with a new random, is still maintained by your computer to hold up established TCP sessions. So if you have an SSH session or an RDP session, or maybe you're logged into vCenter, that IP address is going to be used for your old connections. But if I create a new SSH session, it's going to come from my new IP. So what's kind of neat about this is you could see multiple IPv6 addresses on one box. And they're just going to be changed. And you won't create new connections from the old IP. But the idea here is this is to give you some privacy. The other way to do this was EUI64. This is the one that looked really clever, but turned out, unfortunately, to be a little bit evil. They take your MAC address, which is 48 bits, they put 24 bits here, 24 bits here, and fill the middle with 16 more bits, FFFE. That gives us a 64-bit host identifier. The problem is this never changes, so every download, every query, every email, every purchase, every transaction you never ever make online, every torrent you download would always be tracked to your exact laptop on your exact network. And for most people, remember, Google, Facebook, all that stuff is free. All of our mobile apps are free because people just want to monitor and track you. So this seemed really clever at first, but it turned out to not be such a great idea, which is why Microsoft randomizes your IP addresses. So a little bit off the deep end with IPv6 addressing, but hopefully that served as a good refresher. We got to understand it before we can troubleshoot it, right? So that's just kind of defining our address format. We also have a loopback, not a loopback, I'm sorry, a link local address. And this is what you see even if IPv6 isn't really working. So for example, I shut off IPv6 inside of our network, but I leave it enabled on this host so I can talk about it in class. So for example, if I come over here and I say ipconfig/all, and I look at my main example interface, 10.127.127.62, if we see what happens here, he has an IPv6 address, and notice that it says preferred. If you had an established connection and this changed, it would roll back and you'd see like 2 IP addresses, and there might be one that was deprecated. But this is the address that we're using currently. The FE80 address is used for local communication in your broadcast domain only. The weird thing is they tell you that IPv6 doesn't have broadcasts, but you're still in a broadcast domain. You're still inside of a VLAN, and you get connected by routers which don't forward broadcasts. So a link local can be used for communication within the VLAN only. This is used by some more advanced protocols. So for example, if you have 2 routers and they're going to form an adjacency using OSPF, OSPF is going to form an adjacency using these FE80 addresses. The adjacency is unique to this particular broadcast domain. And the cool thing is I could change my IPv6 address from one value to a second value, and it won't break my adjacency because the adjacency is based on this set of addresses, which isn't really routable. We don't really use this for normal traffic. So it allows us to form an adjacency, change our address, and we didn't disrupt the OSPF adjacency when we did it. That wasn't why they created link local. They created link local for inter-process communication on a particular broadcast domain with the intention that it's not going to be routable. Sounds a little bit weird. Why do we care? Because routing protocols form adjacencies using these addresses. Windows hosts have FE80 addresses as well. That's what I was just showing you. And for every interface that you have that IPv6 enabled on, you're going to see an FE80 address on that interface. All right. So looking at what we see here, this is an example of EUI64, right? We take the MAC address, which is 48 bits, we add 16 bits to the middle, voila, 64-bit address. Inside your first byte, and remember that a byte is 8 bits, the second most significant, least significant bit right there actually means something. If it's set to a 1, it means this value is universally unique. If it's set to a 0, it's locally unique. Well, all we're saying here is that this is a universally unique value. So the 0 will get changed to a 1, and it changes a 0, 0 to a 0, 2, because in binary, that second bit has a value of 2 if it's set to 1. The dangerous thing here is I could look at somebody's IPv6 address. I could look at that 029027, and I could change it to 009027 and go, oh, that's a Cisco prefix. That's a Cisco device I'm looking at. So if you were to use EUI64, anybody could look at your MAC address and then go, oh, that's an OSX-based Mac laptop, I bet, because the MAC address belongs to Apple. It's a Mac. You could tell if something was based in VMware, because VMware has their own prefix for the first 24 bits of MAC address. So because a modified version of your OUI is present there, this isn't something that I recommend that you use. Plus, there's going to be privacy concerns, right? So even if you don't care if people look at what you browse, you care if you're being targeted, and somebody could determine what platform you're on by looking at that address. All right, so outside of the addressing format, how different is it to troubleshoot? Well, when we go to troubleshoot, we can use ping and we can use traceroute the same way that we always have. We talked about these a little bit yesterday. I said we can't always trust ping because sometimes ICMP is blocked. We talked about how traceroute is just a hack because we're looking for ICMP error messages to come back. And whoever generates the ICMP error messages is the particular device that's that many hops away. We use the TTL field in the IP header to discover who the routers are. 1 hop out, 2 hops out, 3 hops out, and so forth. IPv6 is no different. So again, just showing you ping and traceroute. Other things we can do, you can telnet to an IPv6-based application. It would look like this. And then you could telnet there and specify the application as a port number. Remember, we talked about this yesterday. This is how we can verify that we can reach an application. And when you get there, instead of a telnet prompt, you might see some HTTP messages. Like in this case, we see a 400 error coming back to us. So that's really not any different. One of the things that is a little bit different is we don't have ARP in IPv6. We have something called ICMP, neighbor discovery. We also don't have broadcast in IPv6. Not technically, there's not an all Fs address, but we do have multicast, and there's even a multicast that's called all nodes. And that would do the same thing as a broadcast. So when people say there's no broadcast in IPv6, I always look at them a little bit funny. I don't know, because you can still pull it off. Anyhow, we send multicasts out to perform ICMP neighbor discovery. I can basically send out a request that says I'm trying to find what IPv6 address, and you'd specify the IPv6 address, is located at a particular MAC. So in other words, I know the v6 address, but I don't know what the MAC address is. So we send out a multicast to discover that. And what happens in response to this is called a neighbor advertisement. It's basically ARP, but it's called neighbor discovery. An ARP request is a neighbor discovery. The ARP reply would be a neighbor advertisement. What they're doing in Windows is saying netsh interface IPv6 show neighbor, and this is viewing what would be in IPv4, or in our vocabulary, ARP cache. I see that this IPv6 address equals this particular MAC address. You can do a show IPv6 neighbors on a router, and these are the neighbors that he's learned about. This is our IPv6 neighbor cache. This is very much like ARP cache. What we see on the left are IPv6 addresses. What we see on the right are MAC addresses. So we still have to resolve these or we're not going anywhere. This is going to happen automatically. The real problem here is some people feel that they can go into a router, put an ACL, and I watch too many science fiction movies, so I draw my ACL as a force field, like Star Wars or Star Trek. And what we do with our access list is we punch holes to allow specific types of traffic through. A lot of administrators will say deny ICMP. And they don't get specific. When we deny ICMP, our access list is really powerful. We can say deny the specific type of ICMP. So block a type 8. That's an echo request, but you wouldn't want to block an echo reply or you couldn't receive pings. You probably don't want to block destination unreachables, or you're not going to know why you're having errors. You're not going to want to block TTL expired, or you're not going to know that you've got a routing loop. So you want to allow certain ICMP messages in. You just want to block ping. So with IPv4, you'd say deny ICMP, and you'd specify like a type 8. What's going on here is in IPv6, you need ICMP. IGMP, which is how we subscribe to a multicast group, IGMP is gone. DHCP is available, but kind of gone. ARP is gone. So what happens there is we need to use ICMP for router solicitations and router advertisements. We need ICMP for neighbor discovery and neighbor advertisements. We need ICMP for a feature called multicast listener discovery, or MLD. It replaces IGMP in IPv4, which is how we go out and we request a multicast group. So if those were a bunch of acronyms and IPv6 is not your favorite subject, let's just recap by saying ICMP in IP version 6 is really, really important. A lot of our fundamental network needs, things like determining IP addressing and resolving MAC addresses, is handled by ICMP. So you can't just have a blanket statement that says ignore all ICMP. IPv6 has an implicit deny in the ACLs, but above it, it has some implicit permits for ICMP. So ICMP is just going to work without you thinking about it. The problem that you may get into is you go, I'm going to block ICMP on this router. If you're one of those guys that's done that historically, stop. You have to be more specific than that. You have to say, I want to block these types of ICMP messages. And you can look up the codes to see what you want to block and what you want to permit. ICMP in IP version 6 makes a little bit more sense. Let me tell you why. In version 4, your error codes are all over the place. Like a ping request is an 8. A reply is 0. Okay, so echo request is 8, reply is 0. Those are diagnostic, right? What's really important? I go, well, like a type 3 means unreachable. So you probably want those back in, right? So if you look at IP version 4, there's these code numbers. Let me show you. That might be easier than describing it. ICMP error codes. So these are our types, right? Destination unreachable is a type 3, which is something you probably want, but echo request is something you may not want. Believe it or not, IPv4 had router selection, they had router advertisements. These might be things that you don't use. So what you do is you would look through this list and you can allow specific types, and each type even has particular message codes. So you could allow type 3, and then like a code 13 is communication administratively prohibited. This means it's being dropped by an access list most of the time. 4 means fragmentation was needed, but you had the don't fragment bit set in your IP header. So you could allow specific message types and even specific codes through. The moral of the story is in IP version 4, there's a hodgepodge of queries. Like you can do an ICMP echo request. Look at this. Did you know you can do an IP subnet mask request? I can send a query to a remote host and go, hey, what's your subnet mask? And it'll go, who, me? I'm in a /28. This could be used for reconnaissance purposes. So maybe you want to block these particular types. The weird thing is your diagnostic messages are mixed in with your error messages. If you look at ICMP v6 error codes, they organized it a little bit better, because what they did was they put all of your error messages from 127 to 0. And then 128 and above are all of your diagnostic things. So things like echo request, echo reply, neighbor solicitation, neighbor advertisement, route solicitation, router advertisement. All those are above 128. So if you go, I want to block things coming from my service provider, 128 and up would be okay. And then everything below, we can go ahead and let in messages like packet too big. It tells us we need to do fragmentation. We can see time exceeded. So TTL expired in transit type messages we can see. We can see destination unreachable type errors. So we can see particular messages that refer to errors and separate them out very easily from our diagnostics. 127 and below are errors. All right, so probably more than you cared to know about ICMP and IP version 6, but we're in good shape. Hopefully everybody's comfortable with that. As always, routers are about path selection, so we can validate that our routes look good by doing a show IPv6 route. The way that you read this is on two different lines because the addressing is so long. So what we see here is a static route. That's shorthand for a default route. 1 is our cost. Static routes have an administrative distance of 1. And then here it says via, this is the next hop. So it reads the same way that an IPv4 routing table reads. It just looks a little bit different. As far as doing an IP config shows you both your v4 and your v6 addresses. Don't be surprised if you have multiple IPv6 addresses. Windows will do that, and it'll change them throughout the day to give you a bit of privacy. Additionally, you'll have a link local IP address, and this is going to be used just for inter-process communication that exists within your broadcast domain. So certain applications or certain, like for us, routing protocols would be the first thing that you saw that would use this. Name resolution, if you're like me, you probably, I hope you're not, but you probably type faster than you think sometimes, and maybe you do some typos. If you can screw up an IPv4 address, you can definitely screw up an IPv6 address. So DNS is going to be more important than ever. We can use DNS for IPv6. I always show people this, that whether or not you're realizing it, like see if I do ipconfig, you see that I've got 2 DNS servers, and they're both right here. They're IPv4 DNS servers. Look at what happens if I look up facebook.com. It's going to tell me an IPv4 as well as an IPv6 destination. So even though I queried an IPv4 DNS server, this is just the transport, right? On top of this is a UDP header that gets me to the DNS service. Inside of that is a payload saying Ryan wants to know who facebook.com is. So it's in the payload that they give me a quad A record, which is an IPv6 answer, and an IPv4 answer. So the thing you have to be careful about is if somebody types in a domain name, like yahoo.com, and they say, I can't reach yahoo.com, realize that your domain name server is sending them very likely a v6 address and a v4 address. And if that user has a global IPv6 value, not link local, but a globally routable, it's going to start with a 2, probably 2001 or 2600 in North America. If you've got a value that looks like this on your computer, you're going to try to use IPv6. He prefers v6 to v4 whenever he can use it. So this is about troubleshooting. One of the things to keep an eye on is what are we resolving a domain name to? We can also do static mappings. So again, kind of poking fun at myself, I would totally screw that up. If I typed that 4 times in a row, I would get it right probably twice. So I can get it right 1 time, and then I can call it server 6. And then in the future, I could just say ping server 6, and it would go ahead and resolve that name for me. Make sense? They're showing it here from a command line in Windows, but it will work the same way in iOS. As far as ACL issues in IP version 6, I mentioned earlier, you got to watch ICMP. Make sure we permit this. In this scenario, they're only allowing ICMP, so obviously Telnet wouldn't work. We need to support TCP as well as UDP. From a high level, don't be scared of this. Access list is an access list. It's processed from top to bottom with an implicit deny at the end. The thing that you've got to remember is certain ICMP messages are required, so don't try to block them all by default. The other thing you've got to remember is, let's just bring up a whiteboard. Let's say that today I'm going to get real motivated and set up IPv6 inside my environment. I talked to Hurricane Electric. They assigned me a /48. So over the IPv4 internet, I build a tunnel to Hurricane Electric. And these guys are part of the IPv6 internet. So my service provider doesn't give me an IPv6 connection. So I get IPv6 addressing from Hurricane Electric. I set up an IPv6 over IPv4 tunnel. Basically says take in the IPv6 traffic, encapsulate it in an IPv4 header, send it to Hurricane Electric. They're going to rip off the v4 header and send the v6 header into the internet. This is pretty easy to do. I would say if you tinkered with this and you read on their website and you went slowly and carefully, in 90 minutes, and that's taking your time and kind of reading about what you're doing and understanding it, I bet in 90 minutes you could have this up and running. Hooray, you're doing IPv6 and you're on the internet. The downside is your access list on this interface is IPv4. Additionally, you're used to using NAT. NAT makes you secure by default. I say this because you're using private addressing in the inside that can't be reached without some static NAT being configured. No one can get back in. With IPv6, those addresses are reachable directly from anywhere on the planet. Your IPv4 access list does not stop IPv6 traffic, and the lack of NAT means as soon as you turn this on, all of your Windows hosts are now getting a route advertisement from your router. They're forming IPv6 addresses, and they're preferring it to IPv4. So just like you flipped a light switch, most of your traffic is going to start moving through IPv6, which is tricky because your web application filter, whatever you're using for content filtering, may not support IPv6. Your IPS may not support IPv6. And like I said, IPv6 is going to be globally reachable. Anybody can come in and hit any of these hosts right off the bat. So it's up to you to configure IPv6 access control lists that deny that from happening. If you don't, everything's globally reachable. So definitely use this with care. It's easy to set up, but sometimes people don't realize what they just did. They're used to NAT being there, they're used to their IPv4 ACLs doing something, and they're not. You're globally plugged into one big network with everybody else on the planet. A compromised mobile device in Africa somewhere could have some malware on it and hit your Windows host on the 3rd floor that belongs to your accountant. Everything can talk directly. There is no filtering. Not until you add it. All right. So we create IPv6 access lists and apply them to interfaces just like IPv4. Not a lot to say there. This is an example of creating an IPv6 named ACL. Hopefully it shouldn't look too scary. And if it's applied to a router interface and it's doing traffic filtering, we would see matches that look just like this. All right. So that gives us a wrap on IPv6 troubleshooting. And that's going to close out that particular chapter within our book. We'll go ahead and take our 15-minute break. And when we come back from the break, we'll jump into EIGRP. Now, I hope everybody's doing okay. I know it's Friday afternoon and you might be ready to unplug the brain a bit, and IPv6 is maybe not your favorite topic. The things that I went into this afternoon were just additional detail for you. The CCNA exam is not going to test you extensively on IPv6. You'll probably need to know the formatting. You need to know that ping and traceroute can utilize it. You want to know the difference between an FE80 address and a globally routable address. But for the most part, they're not really going to beat you up on it. I just gave you a little bit of extra information here because I know IPv6 really well. I used to teach a dedicated 40-hour class on just v6. So just trying to give you guys some pointers because you may not pick it up elsewhere. But definitely don't feel overwhelmed or discouraged. Just think of it as a value add that you can take or leave. We'll go ahead and we'll take our break now. and I'll see you guys after the break. We'll jump in and do some EIGRP.